The aim of the experiment we're performing today is the calibration of the LVDT, also known as the linear variable differential transformer. So here, this is our experimental setup. We have the micrometer, which is the standard. We have the LVDT, which is our measuring device, and the display meter, which shows the displacement of the LVDT. So this is the lab record where we have measured, taken our observations. So we have mainly...
Show how you take the reading, how to switch on the machine.
Okay. So this is the main switch. On. So right now our LVDT is at the null position, so it's showing a 0 reading. So how the LVDT works is there is one primary coil and two secondary coils, and the two secondary coils are connected in opposition to each other. So the reading, the output voltage is determined by the position of the core inside the LVDT. So when there is a displacement of the core to either the left side of the null or the right side of the null, reading is shown here. So initially it is at 0, the core is at null position, so the reading over here is 0. So when there is a displacement in the micrometer, the core moves to one side, and thus there is an extra voltage which is induced in one of the secondary coils. So this induces a voltage which is shown over here. So we'll go to the observation thing. We have mainly three learning objectives: the importance of the calibration, the measurement of error, and how the LVDT works. And this is our observation table. We have the core position, which is one to the left side of null and to the right side of the null, as there are two secondary coils. We have the displacement meter reading, which is this screw gauge reading, which is our standard, and our correction and error. So we'll start off. So first we move the micrometer by 1 mm and see correspondingly how much
spindle of the micrometer.
The spindle by 1 mm to see and correspondingly check how much the display meter indicates, meaning how much the LVDT records. So the least count of this is 0.01 and the pitch is 0.5. So we need 2 revolutions of the spindle to move by 1 mm. So right now we're going right side of null. So the micrometer has now moved by 1 mm, and our display meter is showing a displacement of 0.91 mm. So the readings can be taken down. And this is 13, and the final reading is 10. So we see that the error is 0.91 minus.
Be louder.
Okay, the error we observe is 0.91 minus 0.09 minus 1. We'll take a few more readings. So same procedure, we'll be moving by 1 mm and seeing how much.
Show me some final tabulations. Just show me some of them. How do you graphically interpret the result? Show me.
Okay, so this is a set of readings we've obtained, and this is our correction error. So the first graph we plotted is the graph of correction versus our measured value. So we see that as the measured value increases, our correction also. We see that as a measured value increases, like 1 mm, 2 mm, 3 mm, our correction also increases, meaning the LVDT becomes less accurate for greater values. And the error is also the same.
What is the percentage error? How does the percentage error vary?
Our percentage error also, there's a very big percentage error. We've obtained a percentage error of or a maximum of minus 9.5%, which is
minimum of
and a minimum of
minus
8%, which is quite high value. So we can conclude that this particular LVD is not very highly accurate. And there's also a plot of the measured versus the standard. So we see that it's almost a straight line. So as the measured, for small values, the LVDT is accurate, but as the values increase, the LVDT becomes less accurate.